Hello, everyone. Welcome to pre-lecture 2. So this will be our first pre-lecture for the semester. We'll be talking about intermolecular forces. And so, of course, where we left off at the end of our first class in class was talking about the different types of molecular forces we have. So those are dispersion forces, dipole-dipole interaction, hydrogen bonds, and then we also have ion-dipole interactions and ion-ion forces. And most of what we'll be talking about in this pre-lecture is the first three of those. Of course, the reason ion-dipole interaction and ion-ion forces are the strongest is because they have a full positive or negative charge involved with them. But we're going to be focusing on the first three that only involve partial charges. Okay? So first of these is dispersion forces. These are the weakest intermolecular forces found within molecules, and they're going to be present in all states of matter. And so because our atom or molecule is always going to be in constant motion, everything within it is going to be moving, including, most importantly, the electrons. And so as these electrons move, they will do what's called create an instantaneous dipole. And so this is when the electrons are distributed asymmetrically. So they might be on one side of the atom or molecule and not on the other. And so the larger or heavier that our molecule gets, the stronger the dispersion forces will be. So atoms that are small or light will not have strong dispersion forces, whereas something very heavy like, say, mercury will actually have a large electron cloud and thus large dispersion forces. Okay. In addition to having this instantaneous dipole, we would say that molecules or atoms with large electron clouds are also easily polarizable. And so that means that you can basically move the electrons to one side or another easily, which again leads to stronger dispersion forces. Okay. So what are the characteristics of molecules that have their intermolecular forces dominated by dispersion forces? Well, they tend to be of a single element. So the examples we have here are from row 17 of our periodic table, or rather column 17, where we have fluorine, chlorine, bromine, iodine, and astatine. And so that's just going down the column. And they're all, again, just one element present, despite there being two atoms. Okay. All of these also contain bonds that are nonpolar. So ultimately, things that are nonpolar, or the most nonpolar, tend to be of the same element, but we could also have things like hydrocarbons that are also nonpolar bonds. Okay. Molecules that might be tricky to identify that only have dispersion forces may have polar bonds, but those polar bonds may be distributed in a symmetrical fashion. So you could think of something like CCl4, where all of the polarities, every bond, every carbon-chlorine bond is polar, but all of the polarities cancel out to zero, meaning that the molecule is ultimately only dominated by intermolecular forces that are dispersion forces. So switching gears from our dispersion forces to dipole-dipole interactions, these sorts of molecules will typically have a partial positive charge and a partial negative charge. So we indicate that with the Greek symbol delta here. So this is lowercase delta, and this would mean partial positive, this would mean partial negative. Okay. And when we get one side that's positive, one side that's negative, we call that a dipole. Okay? And so the polarities are going to be determined by the electronegativities of the atoms that are bonded together, and also the geometry of the molecule. And so again, just a reminder that if a molecule is totally symmetrical, even if it has polar bonds, those may cancel out to make the molecule nonpolar. So kind of a case study would be HCl, hydrochloric acid, and F2. These molecules have approximately the same weight, they have the same number of atoms, but because HCl is dominated by dipole-dipole interactions at 150 degrees Kelvin, the dipole-dipole interactions actually stick the HCl molecules together, turning them into a liquid, whereas F2 will remain a gas due to the only dispersion forces being present, thus less intermolecular forces. Okay. These are kind of our medium strength intermolecular forces. And so some trends to identify these. They must be in molecules that contain multiple elements. They must have polar bonds. And so again, thinking back to our electronegativity, they must have basically a break in symmetry. So you can think of something like CHCl3 as opposed to CCl4. So once we insert or replace one of those chlorines with a hydrogen, we then have one nonpolar bond, making the whole molecule be polar. Okay? And so all of our polarities don't cancel out to zero. All right, and then our last intermolecular force that we're going to be talking about in this video is hydrogen bonding. So hydrogen bonding is really just an extreme form of a dipole-dipole interaction. And it's so extreme that we actually identify it as its own thing. So as the name would imply, a hydrogen bond must involve the element hydrogen. And hydrogen, in order to form a hydrogen bond, must be bound to one of the elements, nitrogen, oxygen, or fluorine. And so these three elements are next to each other on the periodic table. The way I like to remember them is as the NOF monster, NOF. So I hope that can be helpful in remembering these. They are a very strong intermolecular force, but I would like you to keep in mind that these are still only about 5 to 10% as strong as an intramolecular bond. So that would be, for example, this bond between a hydrogen and an oxygen, as opposed to our intermolecular bond between the oxygen and hydrogen. Okay. And so another thing with hydrogen bonds is that you need two molecules in order to have a hydrogen bond. So you need a donor and an acceptor. If we were looking at this example here, I'm going to go ahead and draw on the slide here. So we would label this hydrogen as our hydrogen bond donor, and this oxygen as our hydrogen bond acceptor. So typically what you'd need to see there, and we can draw them in, is a lone pair. So your hydrogen bond donor will always need, or acceptor rather, will always need a lone pair. Just gonna clear those. Right, and so typically, again, your donor will be either NH, OH, or FH, and then your hydrogen bond acceptor will be something with a lone pair. Water is an exceptional case of a hydrogen bonding molecule because it can accept and donate two hydrogen bonds at the same time. That's a lot of what gives water its very special and privileged properties, as well as things like making life possible. So we appreciate you, water. Right, that'll be it for our pre-lecture for today. If you have any questions, please feel free to email. Otherwise, thank you for watching. I'll see you in class.